So Dean is going to talk about fast spatial analysis and kriging on the grids. And he did graduate studies in applied math, currently living in Vancouver, and did his PhD on pine beetle outbreaks, focusing on practical questions. Where and when will the next outbreak occur? What will be the size of the endemic population? And currently he is in the final years of a MITEX postdoc and working with the Yellowstone Ecological Research Center and the University of Alberta. And also beyond the package that he's going to talk about today, he's also working on some other hydrological, highly spatial simulation engine that is related to that SWAT software that USGS is using, if I'm correct. So I'll let Dean take the reins and maybe correct me if I said something wrong here, but maybe do a bit more intro about yourself. Thank you.
Well, thanks, Peter. And thanks everyone for attending. It's always nice to see so many people interested in my work. You got pretty much everything right there, Peter. Let me see if I can start my slideshow. I had an About Me page, but you've covered most of it. So maybe before I get into that, snapKrig is the name of the package that I'm going to talk about today. And this is a reference to the fact that it's snappy, that it does kriging, but also the fact that you're probably going to have to snap your data to a grid because this is a package for gridded data spatial analysis, data that lie in space on a regular grid. So first, just a little bit about me. Previously, I'd worked on mountain pine beetle spread, but with the help of Subash, I kind of got more interested in the data analysis side of things than the theory that I originally started out working on. And so nowadays, that's had a big influence on what I'm interested in. And my current project, which is a MITAX international postdoc, is all about watershed dynamics and how we can use simulations to create forecasts of what the stream is going to do or what the river is going to do in the future by feeding weather forecast data into the model as input. This is, as it turns out, this involves quite a lot of spatial interpolation, not just of the weather inputs, but when you're simulating the water cycle, you have a lot of earth sciences information to keep track of things like soil properties and vegetation cover and so on. So I've been very much focused on this problem of spatial interpolation for a few years now. And snapKrig is the product of that. snapKrig does a few things, but it focuses on the problem of fast spatial prediction in the domain of two-dimensional spatial grids. So start with a high-level explanation of what that is and what the output looks like. The basic idea is to take observations of a random variable in space, call it Z, and use those observations to get accurate predictions of Z at unobserved locations. And with snapKrig, the data have to be on a grid. So the observations and the predictions both have to lie on the same shared regular grid. So a good example of this kind of problem is downscaling a raster. And here's an example with some data that I worked on in my grad studies years. This is showing pine tree density, an aerial view of pine tree density over a several kilometers wide box. And we start with a quite coarse data set. There's not very much spatial detail. And then by finding covariates related to pine tree density, we're able to downscale this and resolve quite a lot of detail from this coarse input. And we get this very detailed output. The problem with spatial prediction is it can be very, very slow, depending on how many points are involved. And in a problem like this pine tree example, there are quite a few points. We have over 1 million prediction locations in the raster on the right. And this will slow your computer down to a crawl if you're using the wrong methods. And in many cases, it just won't work at all because you'll run out of computer memory. So I wanted to talk about why that is and how snapKrig solves that problem. Before I get into that, I just wanted to show this second example, which is an example of a point interpolation problem that didn't start out on a grid, but we snapped it to a grid. So you might have seen this data before. This is the Meuse River soil data set, and it appears in vignettes for a couple of really common spatial R packages. So you may have seen this before. We go through this example in quite a lot of detail in the R journal paper submission that Peter mentioned. So hopefully in a few months, we'll have that published, and then I can share a link to that more detailed explanation of soil zinc interpolation. But I just wanted to show you this example because while snapKrig is limited to grid data, you can often massage the data into a form that that works in that context. So as I said, spatial prediction can often be very slow. And this plot illustrates that by comparing the time to evaluate spatial predictions for several different packages over a range of different problem sizes. So on the x-axis, we have an increasing number of points to predict. And I've highlighted where that pine tree example falls on this axis. And you can see that things get very slow most of the time with conventional R packages. And this has to do with the way that we evaluate the kriging prediction equations. So I'm going to get into details of that. But first, I just want to point out the problem here. It's not just a matter of convenience. Obviously, it's inconvenient to be waiting for hours for your computer to finish crunching the numbers when you're just trying to do some data exploration or something. But it's more than that. Quite often, it's not just a matter of things becoming slow. Your computer will sometimes run out of memory, and then you'll hit an error. And so then you can't actually get any kind of answer. So snapKrig is meant to not just make things faster, but also raise the ceiling on the size of problems that you can solve. And so in this example, the pine tree spatial prediction problem took just over a second, whereas the nearest alternative implementation takes closer to several minutes to complete. So we're looking at an order of magnitude or several orders of magnitude improvement in compute times. And so I want to try to explain how we do that. And before I do that, I want to just show you some snapKrig code. We put a lot of time into trying to develop a good class for grids that's convenient for me to work with mathematically and also convenient for the user to interact with in terms of changing things and displaying things in a plot. So I have the SKgrid class, And here's some example code showing how to define a grid object based on its dimensions, and then fill it with some data. And in this case, I simulate data, but you could also open your data from a file like a GeoTIFF, or copy it from an existing R object like a spat raster or raster object. Or you can just create one from a matrix of values. And we'll see some examples where I use snapKrig and its plot method to visualize a matrix. And I actually find this very convenient as a mathematician to be able to do that quickly, because it can be a little cumbersome with the default base R image plotter. So how does this work? The basic idea with spatial prediction in the field of geostatistics is that proximity introduces spatial dependence. And this is something that was kind of explored empirically by a man named Dean Koch, who was a mining engineer. And so that's why the technique that I'm talking about is called kriging. It's kind of an unusual name. I don't know of any other names where someone's taken someone's last name and added ing at the end, but that's the name we're stuck with. So that's what kriging means and why we call it that. But there's a whole theory behind kriging and this idea of proximity introducing dependence. And in short, the theory says we should be assigning more weight in our predictor to the observations that lie closer to the point we're predicting at. And this is very succinctly expressed in the inverse distance weighting formula. So if you've done any spatial data analysis before, you've probably played with this algorithm before. It's very simple. You're just taking a weighted average of the observed data, and you're weighting it by the inverse of how far away it is. The geostatistics-based version of this is called kriging, and it's a model-based approach. So it doesn't start from this formula. Instead, it starts from basic assumptions about the spatial process that generates the data. And if we assume that it's a Gaussian process, then it turns out that the optimal predictor can be derived exactly, and it has a very simple mathematical form. And this makes the technique very appealing mathematically, and it makes things a little simpler in practice. I'm just going to close my blinds because I got the sun in my face. Okay. So this technique of deriving the optimal unbiased predictor is called kriging. And I'm just going to show you the simplest form of this, which is called simple kriging. And this is where we're assuming that the mean value is fixed and known. And in that case, the optimal predictor looks like this. Has a very simple looking form, simple algebraically. We're just taking a row of the covariance matrix, multiplying it by the inverse of the covariance matrix, and this gets us our weights, our kriging weights, in order to form that weighted average in our predictor. But the reality is that this is simple algebraically, but computationally it can be very difficult. And the reason is that this matrix V is n by n, where n is the number of observed data points. And sometimes our observations, our sample can be quite large. So we can have a very large n. And it somewhat surprisingly can grind your computer to a halt when you have even a moderately large problem. And this is particularly true when your input data forms a grid, because at least for me, a smallish looking grid has a surprisingly large number of points because the number of points is the square of the side length. So these matrices get very big very quickly. And here's an example where I'm trying to copy the covariance matrix for a 500 by 500 grid. Just an example with some example parameters. And I get this error from R that says it's trying to write a vector of size 400 gigabytes. This has always been surprising to me. It doesn't seem like that's a big problem, but it is. We can't create this matrix in computer memory, so we need some other way of solving the problem of evaluating this predictor equation. And the trick with snapKrig is that we use a particular model for the covariance in which the covariance matrix V becomes a Kronecker product of two smaller covariance matrices. So we would write Vx and Vy for the smaller matrices, and their Kronecker product we denote by this kind of circle multiply symbol. The reason we want to do this is that there's this whole set of very convenient mathematical identities that becomes available to us when V is structured this way. So, for example, this isn't actually the main identity that is crucial for snapKrig, but this is a good example to illustrate. If you want the inverse of V, you just take the inverse of the components and take their Kronecker product. The reason this is so useful is that these component matrices are small in dimension. The dimension of V is equal to the product of the dimensions of the components in the Kronecker product. So here's an example where I'm plotting some matrices as heat maps. And the covariance matrix that we want is 18 by 18. This is showing us the covariances between all 18 points in a 6 by 3 grid. And we construct it by defining these two component matrices, one for the y dimension and one for the x dimension. And these components have dimensions 3 by 3 and 6 by 6. So if inversion or factorization or whatever you're trying to do to this matrix, it costs you order n cubed operations, if that's the algorithmic complexity, and you're able to reduce this to a pair of smaller problems where you have n equals 6 and n equals 3, that can make a huge difference because of this cubic complexity factor in matrix operations like inversion. Now, if you've never seen a Kronecker product before and you're not sure how it works, I'm not going to define it mathematically, but I have this image to try and show what's happening. Basically, the matrix on the left of the product, the Vx, is split into each of its individual matrix entries, and we take the first entry and we multiply that number by the entire second matrix, and we place that in the top left block of the output matrix. Then we repeat that for the next entry of the component matrix of X, multiply that second entry by the entire matrix V and place that in the second block, and so on until we get this block matrix on the right with this very regular structure. It's that regular structure that gives us all these nice identities, which include a whole bunch of computational shortcuts related to prediction. Now, this Kronecker product structure is guaranteed when we have gridded data and we use this special covariance model However, quite often in real problems, we're going to be missing some data. So our data might live on a grid, but it's not a complete grid because there's one or two observations missing, or maybe a few more. It actually doesn't matter how many observations are missing. As soon as you have any missing data at all in your grid, you will most likely lose that Kronecker product structure. And so I have another visual example here to illustrate that. On the left, we've got a 25 by 10 grid, and we can construct a covariance matrix for all the points in that grid. And it might look like the heat map on the left, 250 by 250 matrix. You can see the structure, the block structure, the banding. There's a lot of symmetry in this matrix. Now, if we go and take points out at random and we say that there's only 50 points in this grid that are actually observed, the covariance matrix under the Gaussian model becomes just the submatrix of the one on the left, with all the rows and columns corresponding to the observed data. So you basically take the matrix on the left and you chop away some of the rows and columns, and what you're left with is this matrix on the right. And you can see that there's still some structure there, but it's not as regular. And unfortunately, this means we don't get to use these nice Kronecker product identities anymore, unless we do some clever tricks. And so part of the magic of snapKrig is finding a way to use the Kronecker product in situations where we don't have the Kronecker structure in the matrix we're working with, but we can somehow embed the problem in another one where we do have that structure. And so just to illustrate this difference between the complete and the incomplete case, here's another benchmark graph. This is showing the fields GOR and snapKrig packages and their evaluation time for the likelihood function. And we have, for each of these packages, 2 lines. The solid line represents the case of the complete grid, and the dashed line, the incomplete, or sorry, vice versa. Incomplete grid is solid line, dashed line is complete. And the takeaway from this plot here is that every implementation I've looked at has the same kind of growth curve in evaluation times as our sample size gets bigger, except for snapKrig on the complete grid case. And that is because we are using this Kronecker product trick in that case. And you can see it speeds things up dramatically. We can work on problems that are many thousands of times larger than what we might have previously been able to work on using these packages in this context. Now, like I said, there's some optimization we can do with Kronecker products, even when the grid is incomplete. And I've tried to make snapKrig computationally efficient in lots of different aspects, not just in using Kronecker products. And that includes doing matrix multiplications with the variance matrix very quickly using a technique called circulant embedding with fast Fourier transforms. This is nothing new. It's something a lot of packages do, but snapKrig does it, and that makes it actually quite fast on incomplete grid problems as well. It's not as dramatic of a speed up as with the complete case, but it's still usable. We use Cholesky decompositions, eigen decompositions as well for evaluating inverses. If you're new to this kind of coding problem, just be warned that you should never try to invert your variance matrix directly. Don't just pass it to solve, or you'll have trouble with numerical errors. And Cholesky factorization is a good way around that. Now, to illustrate what kind of performance advantage you can get in the incomplete grid case, I have an example here. This is point interpolation for a range of prediction point numbers. And you can see that once again, snapKrig becomes relatively fast compared to existing alternatives as we get into the range of 10,000 points, 100,000, 1 million points. In practice, what you're going to have to do if you want to do spatial prediction is probably you're going to have to fit a covariance model. And I didn't think we probably didn't have enough time for me to go into details of the theory about that, but I wanted to show you how this works in broad strokes. So I made this Shiny app, and I'll try to open that now. Okay, so can you see the app?
I can still see the slides.
Oh.
Yes.
How about now? Okay, good. Okay, so what I'm doing here is I'm taking the R logo, just a PNG file, it's just an image at a certain resolution, coarse resolution, and I'm downscaling it by a certain factor. So I can turn this up to, say, 8 times. And so now we're interpolating, we're increasing the resolution and estimating the in-between values using this Gaussian process model. Is the Gaussian process a good model for the R logo? Probably not, but this shows what the package does and how the predictions are related to the covariance parameters. So on the left, you can see I have sliders for something called the nugget, the partial sill, and on the bottom here, range parameters. These are the most influential parameters in terms of the prediction output. And you can see when you increase the range of the X parameter, the whole image becomes kind of blurred horizontally. And we could do the same thing in the vertical direction. And then we have these parameters for partial sill and nugget. And these are controlling the covariance structure of the spatial error and also of the measurement error that we assume exists in all of our observed points. So I'm going to share the code for this. It's not up on my GitHub page yet, but maybe after the talk, I'll share this code so that you can experiment with this a little bit. On the other tab, we have something called a semi-variogram, and above it, a covariance footprint. And so what this is showing is what is our model for the covariance that is producing these estimates. So our estimator just kind of takes the input points and fuzzes them a little bit. It's doing this because we've specified a covariance model where every point is spatially dependent on its surroundings. And this plot is showing exactly what covariance we're assigning to every point pair. So, for example, if we consider the point in the very middle, this is showing us the covariance between that point and its surrounding points. On the bottom is the semi-variogram plot. And if you've ever worked with geostatistics before, you'll probably encounter the semi-variogram right away. It's often how the concepts are introduced. But I actually find it a little bit misleading. And this is an example here where the model we've picked, which is illustrated in blue, isn't really aligning with the sample points from the source image. But that's okay. I think the takeaway I want people to have from this is semi-variograms often aren't great estimators of the covariance structure in your data for a number of reasons. And so they can be helpful for I think learning the material and exploring the data. But when it comes to actually estimating these parameters, these slider values, I recommend that people use maximum likelihood. So let me close this demo. I'll go back to my slideshow. So what I've said in the slide here is you can pick your covariance parameters by hand. And by that, I mean, you could use a semi-variogram and pick the parameters that kind of make your model curve line up with these sample values. But I would argue that that's kind of an unreliable way of fitting your model. So much better to use a likelihood-based method. And snapKrig provides an automated likelihood maximization function. And it's called SKfit. So this just calls the stats optimize function in, or maybe it's optim, yeah, stats optim in base R, and fits all of the covariance parameters to your data so that you can quickly get at least a first approximation to a fitted model. So to illustrate, I'm going to show you some data that I'm working with right now in my Watershed simulation work. And so the goal here is to take some weather forecast data, which arrives as a low resolution grid. And we want to downscale it to get a high resolution version that will be more useful as input to the Watershed simulator. So here's the area that I'm going to look at. And I'm just showing a digital elevation model over the Pacific Northwest. And we're going to look at this region that's in the center, the boxed region in the middle. So I haven't actually run this code in my R Markdown file that made the presentation because it's a little bit slow and there's some data preparation involved, which I've completely glossed over. But all you need to know about this is that grib_rast is a spat raster from the Terra package. And I fetched this from the North Oceanic and Atmospheric Administration's global forecast model called the GFS. And this is actually the forecast from this morning, and it's showing us the forecasted maximum temperature tomorrow at 11. I also include a covariance matrix that that has a column for elevation and a column for the climatic norm, so the normal temperature max that we would expect at this time of year. And these 3 lines of code are all it takes to get a pretty reasonable kriging prediction at a much higher resolution from this coarse global forecast system data. So on the right, I'm showing the source data on top and the downscaled result on the bottom. And here's a detail over the Edmonton area. So this is for 11 a.m. tomorrow. So I'm not in Edmonton, so I don't know if this is reasonable, but I think this is probably normal for this time of year. The point of this isn't to make an accurate forecast of Edmonton, but just to illustrate the kind of problem that snapKrig can solve. Here we're looking at a map of about a 50-kilometer radius around Edmonton. And if I were to try to simulate the watershed of the North Saskatchewan River, I would probably want a lot more spatial resolution in my inputs than what I'm getting on the top here from the source data. So snapKrig gives me a way of downscaling and using other data sets that I have at my disposal to get that higher resolution product. And the whole thing is fast, really, really fast. So this code maybe takes a couple seconds to evaluate. So, oh yeah, I've talked for a while, so I'm going to stop now and just recap. snapKrig uses a novel covariogram model, something that's unusual, not often seen, and not implemented yet in R, to my knowledge. And this allows it to speed up kriging prediction and more. The package is for gridded data. So remember, you have to snap your irregular points to a grid first before you can use it. But it is remarkably fast, particularly if you have complete grids, such as in a situation where you're downscaling. We include support for simple, ordinary, and universal kriging. That just refers to how you're constructing the mean, and whether you're using covariance. And it includes its own custom S3 class for grids with a handy plot method and much more. So thank you all for listening, and please let me know if you have any questions.
Thanks.
Thank you so much. This was a really nice presentation. Please go ahead, mute yourself and ask questions.
I was just wondering what the covariates you used for that weather data.
Oh, yeah. That one was actually just two things. So just the elevation in meters and the climatic norms, which is basically like a multi-decade average for the month of February. And that's it.
Cool, thanks.
Yeah. I find with weather data, elevation is often the most influential covariate that I can come up with. And that's particularly true with temperature data, just because of the effect of mountains, of course, brings the temperature down. Yes, and so question from Ronnie, do I have a method to estimate uncertainty when downscaling? Yes, I do. So I guess I didn't include a slide on prediction variance,
okay.
but so the kriging predictor is the equation that I showed you. I showed you the simple kriging predictor, but there's similar ones for ordinary kriging and universal kriging. There's also a kriging variance equation, which looks kind of similar, involves the same type of matrix algebra, but quite a bit more complicated computationally. Basically, if you have n observations, the variance is going to take you about n times longer to compute than would the prediction on its own. Yeah, so does that answer, I hope that answers your question, Ronnie. Let me know if you have any follow-up. Good, okay. Go ahead.
I was just wondering if you've applied this to some of your older data sets like pine beetle.
Oh, yes. Yeah, good question. So snapKrig is kind of a redesign of some code that I actually wrote or started working on during my grad study days. And so at that time, I was interested in mountain pine beetle population density. So I had a lot of maps of mountain pine beetle activity, and there was some downscaling that I needed to do. But in that context, I used this mathematics in a different way. So I was actually using the same kind of Kronecker product structure to build redistribution kernels, which is it's a mathematical trick that we use for estimating how something spreads around through space, kind of like if it was diffusing. And it turns out you can use a lot of the same mathematical tricks in that situation. So I haven't used snapKrig on mountain pine beetle data yet, but I have used similar techniques on that problem.
Thank you. And one thing I wanted to add, I can't quite remember if you've shared the link to the GitHub repo where the package is, but we will after this meetup. And I just wanted to say that if the audience is going to have a look at that, I really enjoyed reading through the code because it looked really nice, and it really shows that this is like a second or I don't know how many iteration, because all just that abstraction is really beautiful and nicely done. So I just wanted to comment on that. And I'm pretty sure that is going to make its use much more like easier or user friendly. So I looked at it and I was impressed.
Thanks so much, Peter. That's really nice to hear. And you're right. This is like the 10th iteration of this code. Like I've worked on it for a while now. And I have tried to make it user friendly. One thing I'm trying to do in my Watershed research is I'm trying to coax hydrologists away from these statistically unfounded methods like inverse distance weighting onto something more principled like kriging. And it's a really hard sell because it's not easy a lot of the time to do kriging. The other packages I showed in my presentation are excellent packages, awesome packages. By no means trying to knock them, for being slow. They're way more complete than snapKrig is, but I did want snapKrig to be easy, like 2 lines and you're done. If all you need is a simple downscaled version. And at the same time provide that statistical rigor to the people who are interested in it. So anyway, hopefully I struck that balance, and I'll provide the link to the GitHub in the chat right now. And I think maybe I don't have the Shiny app up yet, but I'll add that to my repository very soon, so you guys can try that at home. If you want to try it right now, you can just send me a message and I'll email it to you.
And I will also follow up so that we can exchange slides and links, and then I can post it on the website so that we have all that backed up.
Okay, great. Okay, and then we have another question. For the climate interpolation and the like, can you include multiple covariates? And if so, is there a limitation on how many? That's another good question. There's technically no limit, but I will admit I have not tested more than 2 covariates. So if something goes wrong with more covariates, I might not be aware of that. But in terms of the theory, there should be no limit. in terms of computational efficiency, I don't think it would be a problem to have lots of covariates, you know, to a point. Like less than 100 covariates, I'm going to say is probably okay. I think probably what happens is if you're working on a really big problem and you have a lot of covariates, you'll run into the issue that you can't fit the entire data matrix in computer memory before you'll run into any issues with computations. So thanks for that question. Is there anything else people want to ask?
Looks like from the chat that everyone really liked your answers and the package and what it's capable of. And I hope that people are going to give it a try and report back anything that maybe they're stretching the limits of it, and we will know. And or any issues or questions they might have which might benefit its development.
Absolutely, yeah. Please try and break this package and then report back. I'd love to get feedback, and I'd love to know where the weak spots are.